All right, well, let's start by looking at an example here. In this case, we have a 40 millimeter diameter rod cantilevered out from the wall with these multiple loads on there. 1500 Newton load pulling on it, a 600 Newton pulling it down, 800 Newton pulling it in that Z direction, and 100 Newton meter torque. And we're trying to find the stress tensor at point A, or all the stresses from those loads at point A. So the first thing that we would want to do here is look at the statics to find out the forces and moments on that cross section. So I would start by drawing a free body diagram, something like that. So you can see I cut it right here at point A. A would be here. B is on the bottom somewhere. I'm not going to put that in there because it's going to get kind of complicated, or I don't want it to get too messy. Now I want to say, what are all the forces that could be existing on this cross section? Well, there would be a force in this x direction. Now that force is an axial force, so I'm going to label that P, because we've been calling our axial forces P. I could also have a force along this y direction, and because that is parallel to the plane, that would be a shearing force. So I'll call that shearing force in the y direction. And I have a second shearing force in that z direction, v sub z. So I could also have moments here, and I'm going to draw all these moments as positive. I'll figure out the direction later, but using my right hand rule, and I know this coordinate system's wonky. I don't know why they put the x in that direction, why is it, whatever. But I'm going to put my thumb on the positive x, and I'm going to say there's a moment about that x-axis. Now, because that moment is along the length, what we call that is a torque. So it's getting really crowded over here. We'll move my P up here. So I do have a torque. Now, my moments on the Z and the Y axis are more classic, where I just have a moment or a twisting about each axis, Y and Z. So I end up with these 6 unknowns. And 3 forces, one being axial, which I'm calling P, the 2 other being shear, and 3 moments, one of the moments being a torque. So now I'm going to use statics to solve for what each one of those are. And because that should be review, I'm going to move kind of quickly through that part. All right, so taking a look at these statics, as summing the forces in the x direction, what I see is I have a P value of 1500 newtons, and that's in tension. It's pulling on it. From some of the forces in the y, I get a Vy of 600 newtons. And I have it pointing up because the 600 newtons external force is pointing down. And then from some of the forces in the z, I ended up with a force in the z, or shearing force in the z, of negative 800 newtons, or in the negative z direction. From some of the moments about the x-axis, that's where I get that torque. And I have a torque of 100 newton meters. And I converted that into Newton millimeters, since we're going to be working in newtons and millimeters throughout. And notice I did put a negative, meaning just based on the sign convention. Actually, I take it back. That should be a positive. That doesn't really matter too much. It's just a matter of making sure you know which direction it's going when we actually put it into our stress equations. A moment about the y-axis gives me my moment about the y of 240,000, or negative 240,000. And moment about the z is negative 180,000. So the next step that I would probably do, since I'm going to have to use this a lot, is I'm going to go ahead and look at the section properties, meaning I know that the rod has a 40 millimeter diameter. So because I'm going to have to use these a couple times, I'm just going to jot down my section properties over here to the side. And bam, there you go. So area, cross-sectional area, pi over 4d squared, 1256.64. Moment of inertia for a circular solid cross-section is pi over 4 c to the fourth, which is 125,664. Polar moment of inertia, pi over 2 c to the fourth, is 251.3, or sorry, 327 millimeters to the fourth. And lastly, and probably the hardest one, is that Q value. Remember, Q is the, and I have a little diagram, I don't know if you can really see it or not, but if I were to think about a cross section, Q would be the area above that where I want to know the where the neutral axis is, the maximum amount times its y bar prime. So I have half of a circle, pi r squared, and then 4 over 3 pi is the centroid of a half circle. So I end up with 5,333 millimeters cubed. So after I have my section properties, the key to these problems is to go one by one through each one of these forces and moments and say, does it create a stress? If so, what is the magnitude of that stress and what is the subscript? So let's start with the px of 1500 newtons. So if I have an axial force of 1500 newtons, then I know my equation, sigma, is equal to P over A. So I have 1500 newtons over the cross-sectional area, which was what, 1256.64, and that gives me a stress of 1.194 megapascals. It is positive because it is in tension. The one other thing I have to watch out for, or I have to put in here, is my subscript, right, under that sigma. Remember, that's face and direction. So my face over here, and in fact on all of these it'll have the same face. The axis that's perpendicular to this surface is the x-axis. So I would have an x, and then anytime I have a sigma, which means axial stress, I'm pulling it in that x direction, so I had a sigma x. After that px is done, then I can move on to my second, which says Vy is 600 newtons. Now here's a trick to solving these problems. What you want to do is you want to say, well, what would it look like in a 2D context? Because 2D is way easier to think about than 3D. So you have to put yourself in here somewhere, either on one side or the other. I'm going to draw my little guy over here and say that I'm looking at this thing, happier guy, looking at it from that way. So I have Z is going to my left and Y is going up and A is to my left, B is down. And then I'm going to put these shearing forces and moments to get a better idea. So if I'm looking that way and I were to draw the cross section, then I have something that looks like this, where I have, as far as my axes going up would be Y, and I have Z pointing to my left. And in this case, we have a shearing force that is 600 newtons in that positive Y direction. So I have a shear force of 600 newtons. And I have to say, well, would that create a stress at, what are we looking at, point A? Well, where is point A on this thing? Point A is right on this z-axis. So here's my point A. And the answer to that is yes, it would create a stress. The reason I know it would create a stress is because we've drawn this stress profile a number of times now. We said it's parabolic, maximum at the midpoint, and then approaches 0 at the top and bottom. So up at the top, if I were looking at a point up at top or bottom, it would be 0. But because I'm at point A, I do have a shearing stress, so I have to look at that Q, which is the area, my A prime y bar prime. The equation for that is tau is equal to VQ over IT. Well, my shearing force is 600 newtons. Q, I do have exactly what I just found up there, 5,333 over the moment of inertia, which I found to be what, 125,664. And then the thickness. Remember, the thickness is where I want to know the stress. So the thickness is the diameter in this case, which is 40 millimeters. Multiply that out, and I end up with 0.6366 megapascals. And I'm leaving it as positive because it is pointing in that positive y direction. I'm just saying the same direction as that stress. So that's my Vy value. Two of them are down. The next one is my Vz is negative 800 newtons. So once again, what you're going to want to do is draw that same cross section. Once you draw it once, it's easier the second time because you still have the same axes. Y going up, Z to the left. Point A, which I'm concerned with, is right on the side here. Now we're saying my force is going this way, and I have 800 newtons. And I want to say, well, does that create a stress at point A. So in essence, what you need to do is you need to turn your head sideways from what we just did, meaning this is my neutral axis right along here, right? And remember that my profile would be looking sideways, so it looks like that, where my maximum shear stress would be at the center, and then it decreases to 0 at the top and bottom. Well, A is at the top of that thing, or to the left. It depends if you turned your head sideways or not. So I know that my tau is equal to 0, and that's because Q is equal to 0. All right, I hate to jump around, but there is one little thing I forgot up on the last one. Vy is 600. What about that subscript? Like I said, all of these will be on the x face, and as I say what direction, it's pointing in the y direction, so this would be x, y. This is 0, however, it's still on the x face, and it is pointed in the z direction. So if it had a value, it'd be x, z, right? So there's three of my forces now, and then the next one would be the torque of 100,000 Newton millimeters. So let's try that guy out. So once again, I'm going to start by drawing my cross section, and on this cross section, I'm going to put in my axes. So we have y, z, a is right here. Now the critical point is, which direction is that torque going, right? So if I look at what I'm looking at now, I've been doing reactions, meaning if I'm looking this way, which I am, and I think about a reaction to that torque, it is going, and I'm looking that way, it would be going counterclockwise, right? So my torque is actually going like this. And that torque has a magnitude of 100,000. So what would happen to my shear stress is anytime you have a torque, it basically pinwheels around. The easy way to think of it, it's tangent to the surface. So this is my shearing stress. If I wanted to put a subscript on it, I'm still on the x face because the x is perpendicular to the surface, and then it's pointed in the y direction. So we have an equation, tau xy is equal to Tc over J, the torque being 100,000 Newton millimeters, C value being the radius of 20 millimeters, and J, I think I did J as one of my section properties up here. What is J? 251, 327. So we have J 251, 327 millimeters. I think those were millimeters cubed for J, if I remember right. So plug all that in, and I end up with 7.958 megapascals. Now, if I look at the direction, it's pointing in that negative y direction, right? So I'm actually going to say this is pointing down. I could also say it's negative either way. I just need to make sure that if this is a tau xy, and up here I have another tau xy, am I going to add or subtract those? Well, in this case, I'm going to subtract the two from one another because I have one going up and one going down. All right, so that's the torque. After the torque, what do we have here? We have the moment about the y-axis is negative 240,000. So, just like always, we're drawing our cross section here. Hopefully your circles are getting better than mine. Then my y-axis and z-axis, point A is right here. Well, what does a moment about the y of negative 240 actually look like? Well, it means that it's going like this way. Meaning I put my thumb in the direction of the y, and then I say, I curl my fingers, that's the direction of the moment, and because it's going opposite the direction my fingers would go, then it's going in that direction. So the key here is, at point A, would that moment create a tension, a compression, or is it on the neutral axis? Is it neither? In this case, this is my neutral axis. So you'd have to turn your head sideways again, because what we can see is that A would be in compression. So I have a sigma. My equation is sigma is equal to mc over I. And subscript wise, it's still on the x face and it's pushing into the page, meaning that x direction. So I have a sigma xx. I have MC over I. The moment is 240,000 Newton millimeters. The C value is the radius of 20, and moment of inertia we found up in that section properties to be, looking at my notes, it looks like 125,664. So I plugged that all into my calculator. I ended up with 38.197, and I'm going to put a negative in there because I know it's in compression, right? So I'm not putting the negative in here and following my signs. It gets too complicated. I mean, you could do that, but you're going to really have to pay attention on if this is a positive y or if this is a positive y and or positive z in this case. And I think it just gets really confusing. Positive moment versus negative moment. I think the easiest way is to either draw this correctly the way I did and keep that right hand rule right, or go back to your original and say, if I have this is if you can visually see this. If I have a moment about the y, I can imagine what this looks like. I need my foam example. I'm pulling it about that y-axis. I'm pulling it in the z direction, right? What would that do to A? Would A be in tension or compression? I can see that it would be pushing on A, causing compression. If I were looking at point B, it would be on the neutral axis, so it would be 0, but we aren't. We're looking at A. So you can look back at that to get that sign right, tension versus compression. You can draw it based on right-hand rule, whatever floats your boat, to get that in there. So that's the moment about the Y. What do we have next up here? We have moment about the Z. It's our last one, right? Cool. Just like before, I start by drawing, and then I have my y-axis and a z-axis. Point A is right here. Let me put that over here so I have room to put it, the moment, because then the moment is going like this, right? Well, what can you tell me about A? Is it in tension, compression, or is it on the neutral axis? In this case, it's on the neutral axis. So hopefully you can see that up here, that would be in tension. Down here would be in compression. A is right in between. So I have a sigma. If it was there, it would be xx, but it's equal to 0 because it's on the neutral axis. So the last step in this process is just to add up everything you have as far as your subscripts. So in summary, I have two sigma xx's. I had one from the tensile force of not far enough, there it is, of 1.194 where I was pulling it, so that's in tension, so it's positive. I have 1.194, and then from excuse me, from the moment I have this negative 38.197 minus 38.197. Together that gives me negative 37 megapascals even. That's cool. Now if I go through, the only other variable that I have is tau xy. I do have two of those. Like I said, they are in opposite directions. I have the point 636. Is it 636? 6366 megapascals, and that was positive because it's going in that positive direction, minus this 7.958. That's a point, and that gives me negative 7.32 megapascals. So the last step, if you wanted to do it, would be to put it all into a stress tensor, keeping these straight. I have negative 37 minus 7.32, 0, minus 7.32, and then zeros everywhere else. So I know that was a tough one. If you got it, if you followed even half of that, maybe watch this video twice. I'm going to post another video from a guy who I like on YouTube called Structures Free, and I think he does a totally different example. It's a really good example. It follows more along with what I have for the posted notes on this section. Actually, it's the exact same problem. So watch that. Watch this. Good luck. Oh, really good luck. These things really do blow. I hope it isn't like an hour before this homework's due and you're trying to figure this out. But and let me know if you have any questions, comments, and I'll talk to y'all later. Peace.